Hello everyone, welcome to this video. In this video, I will show you how we improve the power factor or correct or enhance the power factor in a distribution power system. So this is MATLAB. Once you open MATLAB, make sure that you are at the Home tab and then you click on Simulink. Once you click on Simulink, you will have this window and we need to create a new model. So you click on blank model. And here is our space where we can build our model. Again, you can have the components of the model through the library. So for example, we need to have the AC voltage source. So I'm going to Simulink. I'm looking for Simscape and for Simscape electrical. And I'm going down to specialized power systems. And in specialized power systems, I'm going to sources. And here I see the sources that I want. I can reduce the size of the window, and I will select AC voltage source, the one that I need here, and you can drag it to your model. So this is one way how to collect the components. The other way is just to double click anyway in the model and type the name of the component that you want. So I want to have RLC. So I want to have a series RLC branch. So this block, I want to have it. I want also to have RLC load. So series RLC load. So here I have series RLC load. So this is branch, this is load. They are different. I want to have also measurement devices. So in the measurement devices, I need to have voltage measurement. I need to have current measurement. So I'm typing just the first letters of the word measurement, and then I'm selecting whatever I need. So again, I need to have power measurement. So here is the power measurement block. I need also to have RMS block. And I need to have displays. And I need to have three mathematical blocks, which are the product. So, and I need to have divide block, and I need to have a subtract block. So these for some mathematical operation, I will show you why we need them. So I guess these are all the components that we need to have. Of course, we always need to have the Power GUI block, and we keep it standalone somewhere in the system. Okay, so let's start building the distribution system. So of course, we start with the source, and this series branch will model the transmission line. Through this transmission line, we need to measure the current. So this is the current through this transmission line. So let me connect the transmission line to the current source. Okay, so let me do it like this. Okay, so the output to the input of the load. Oh, sorry, this is voltage measurement, so I need current measurement. So I was thinking why it was not connected. Okay, now here we are connecting, and here we are. Then, so this will be the load, the transmission line. I will select to be RL. For the resistance, I will have 0.1, and I will keep the inductance as 1 millihenry. So apply OK. So this will be the transmission line. Okay, and now this is the load. So let me first rotate it. So I want to rotate it in the clockwise direction. So now I will connect it with the transmission line, and I will complete the circuit and connect it to the source. Okay. So for this load, I will double click on it. So I will select the voltage to be 120 volts, and the frequency 60, the active power to be 3000, the reactive power to be 2250, and the capacitive reactive power to be 0. So this will give me a load of a power factor 0.8. So I will do apply and OK. So this is the load that I have. And this is RLC, series RLC load, not a branch load. OK. So now let me do the measurement. So first of all, I need to measure the current. So let me do like this. So you need to make sure that the RMS block is at 60 Hertz, and they are all at 60 by default. So I will do OK. And now I want to have a display to show this current value. OK. And now I want to measure the voltage across the source and the voltage across the load. So I will start with the voltage across the load. So here is the sorry. Okay, here is the voltage across the load. So I will connect this one and I will connect this one. Okay, so this is the voltage across the load. Again, I need to have RMS block. So I will select all these issues, copy, and somewhere here paste, and then I can connect it to the voltage source. Okay, so this will be this will show me the voltage across the load. Let me do it this way. Okay, now I want to have the voltage measured across the source. So I will copy the voltage measurement device. I will paste it somewhere here. I want to flip it. So I will go to rotate flip and flip block left to right. And now I can measure the voltage across this source. Okay, and I need to have RMS block as well, and RMS block and a display. So I will do copy, I will do here paste. So let me see if I can flip them. So copy, look, format, flip or rotate, that's great. So I want to flip them left to right. Okay, that's great. So now I can connect them to this voltage source. Okay, so this to this voltage measurement device that will measure the voltage source value. So the voltage source value, we need to have it 120, but since this is a peak value, so this 120 should be multiplied by the square root of 2. Because here in this block, we have the peak amplitude, and peak is the maximum value. So it will be multiplied by square root of 2. So phase angle is 0, frequency is 60 Hertz. That's all fine. So apply and OK. So now the voltage source had been set, and the load had been set, the transmission line parameters. OK, now we need to measure the power in both places. We need to measure the power at the load side, and we need to measure the power at the source side. So for the power at the load side, what we need to have is the voltage from the source. So we connected before the RMS block, and we need to have the current, and the current is we have only one current in the circuit because it is a single loop circuit. We need to have scopes, so I will do copy and here paste. So this is one scope, and here is another scope. Okay, and we need to make sure that it is 60 Hertz, and here we have only one because we are doing measurement only for the fundamental component. So we don't have any harmonics or DC component. So apply and OK. So I want also to measure the power at the load side. So I want to select all these and copy them. So I will do copy, and somewhere here I will do paste. Okay, so let me have them a little bit above here. Okay, so I will take the voltage from the load side and let me do it a little bit. Okay, and I want to have the current as well, and the current is the same current in the circuit. Okay, so this will measure the power at the load side. So we have the voltage taken from the voltage measurement device, and we have the current is taken from the current measurement device. Okay, so what we need to have the stop time to be equal to 1 second. And let me run the circuit to make sure that everything is fine. So let me run the circuit. So what I see that here we have the voltage is 120 volts, okay? And I see that the power here, the power of the load, it was 3000 watts, but here is to 575, a little bit less, because the voltage applied to this load is less than 120. So if it will be 120 volts, the rated voltage or nominal voltage, then the load will give you the exact number that we had inside it. And for the reactive power here, we had 2250, while here is around 2000. Okay, we see that the current is 28.91 amperes. We see that the power here is a little bit more than this power because we have power which is dissipated in this resistor. And we see that the reactive power as well is more than this reactive power because we have reactive power associated with this inductor on the transmission line. Okay, everything looks fine. Now we want to find the power loss. So what we are losing, what the power that we are losing in the in this circuit. So what we need to do is to deduct this power, the load power, from the delivered power by the source. So here is the delivered power by the source. I will take the delivered power, and here is the power consumed or dissipated by the load alone without taking into account this power. And again, I need to have a display in order to show this value. I will do copy and then paste. So as you see here, I'm using subtract block in order to subtract the load power from the source power. And if I run the circuit, so I see that I have 82.47 watts, which were lost in the transmission line. So this is the lost power. Okay. Now I want to find the power factor. And as you know that the power factor is P over S, and here is P. We need to measure the power factor for the load. So here is P, and S is the square root of P square plus Q square. Or I can calculate as in another manner. I can calculate as VRMS times IRMS. So I have here a product block, and I'm using this product block to multiply the RMS value of the current. As you see, I'm taking the current value after the RMS block. So this is the current value, which is 28.91. And I'm taking the voltage RMS value across the load. So this is the voltage RMS value across the load. So this will be the product of RMS current by the RMS voltage, and this should be the apparent power, And now I want to divide the power by the apparent power. So I'm taking this apparent power to the division block, and the other side of the division block will be the value of the power itself. The value of the power itself, I can take it from here because it's the same value of the power. And then a display block will show me the power factor. Okay. So now this display block should show me the power factor. So let me try once again and run the circuit. Okay, I see that the power factor is 0.8, and this is actually what I'm expecting here. Okay, so let's do some arrangement or let me highlight some blocks that I need to see. First of all, let me give some titles. So this will be the power of the source measured in watts. Okay. And this will be the power, the reactive power of the source measured in volt ampere reactive. This will be the RMS voltage of the source. So I will write VS and comma in volts. So, and this will be the current in the circuit. So it will be I line, comma, ampere. And this block will be the power lost in the transmission line. So P loss, comma, watts. And this will be the voltage across the load, bus V load L, comma, volts. So let me make L capital letter so we can recognize it, okay? And here I will make L as a capital letter. This will be the power of the load. So PL, comma, watts. And this will be the reactive power at the load bus, Q L, comma, var. Okay. So now, as you see that we have all displays. So this will be the power factor, PF. We have all the displays with, let's say, labels. So we can know what are these values. Okay, once again, I want to run the circuit once again. So we have here the power of the source, the reactive power of the source, the RMS voltage of the source, and here we have the line current. Here we have the power lost in the transmission line, which is the difference between two powers. And here we are calculating the power factor as VRMS times IRMS. It will be the apparent power, and we divide the active power by the apparent power, and this will be the power factor. Here is the power at the load bus. Here is the power, reactive power at the load bus, and here is the voltage at the load bus. So what we see here, we see that the current is 28.9. We see that the power loss is 82, and the power factor is 0.8. And here we see the voltage is 110. So I want to highlight these displays. So I will go to format, and I will use background color. And let me select whatever, let me select green. And this one, I want to do the same. So I will go to format and then background color, and I will select green. Okay, so let me undo this. So I want to do again format, and I will select background color. uh, and I will select green. Yes, and then I want to have this display highlighted format, background color, and I will select green again. Format, background color, I select green. Okay, so now I want to select format, foreground color, and make it black. Okay, and now the last one that I want to highlight is this one. So I want to do format, background color, and then I will select it. Okay, so these are the displays that I'm interested in observing during this experiment. So I see the voltage is 110, so we are losing 10 volts as a voltage dropped on the transmission line. I see that the current is around 29 amperes. I see the power factor is 0.8, which is a low power factor. Of course, this is lagging power factor. We can know that this power factor is lagging because we have the inductive circuit, or you can judge by this value. So once this value is positive, then the power factor is lagging. And here we have the lost power is around 82 watts. So now we need to correct this power factor to enhance the power factor or the performance of the system. So what I need to do is to have another series RLC load. So I will copy this and I will paste it somewhere here. And this will serve as my capacitor that I will connect in parallel with the load. So I want to connect this with this in parallel with the load, as you see here. And this will serve as my capacitor. So I will do double click, same voltage, same frequency, no active power, and no inductive reactive power. And for the reactive power, capacitive reactive power, I will start with a value 250 watts. 250 watts. I do apply, I do okay. So here we have a capacitor which is connected in parallel with the load. And we are, let's say, assuming that this capacitor will compensate some of the reactive power required by the load and drawn by the drawn from the source all over the system. So again, let's have a look. 110, 0.8, 82, and almost 29. So we will run the circuit once again. So what we see, the current decreases while you are connecting a capacitor. The lost power decreases, the power factor increases, and the voltage increases as well. So the voltage across increases, which is good. The power factor increases and the power loss decreases, which is also good. So again, we need to increase the reactive power provided by the capacitor to 500. I will do apply, I do okay. Again, let's have a look. 111, 0.83, 77, and 27. Again, we run the circuit. We see that the current decreases more, the power loss decreases more, the power factor increases, and the voltage at the load enhances or becomes closer to the rated voltage, which is 120. Okay, now let me have this reactive power to be 1500 VARs. So I will do apply, I will do okay, and again I will run the circuit. The current decreases to 24. The lost power is already only 60 watts, and the power factor is 0.97, and the voltage is 115. So as you see, as we enhance the power factor by increasing the capacitive value, we see that the power loss is less, and we have a better voltage here across the load, and a better voltage. We see that the power of the load is becoming closer to its rated, which is 3000 here, and 2250 for the inductor. So why this value is as much? because you need to deduct 2250 from this value, capacitor value, and this will be the difference. Okay, now let me do full compensation. So I will do full compensation. So I will say that it's equal to 2250. So the entire reactive power required by the load will be provided by the capacitor. And this will mean that we will have a unity power factor. So let me run the circuit again. And this is actually the case. So we have a unity power factor. We have the voltage is the closest to 120, which is 117. And as you see, the reactive power is almost zero because we do have the full power is compensated. We see that the current is the least, it's 24.4, and the lost power is the least. So this is the importance of correcting the power factor. So you are enhancing the voltage profile at the load itself. You are decreasing the power loss in the transmission system by decreasing the value of the current. And the power factor is, and as you see here, now we have 2,862, which is closer to 3,000, the rated power in this load, because the voltage is very close to 120. So the last issue that I want to show you here, what if I'm increasing the rated or the reactive power provided by the capacitor to be more than required? So I will do 3,000 here and apply OK. So I will run the circuit once again. So what I see the current increases. The current increases. I see the power factor decreases, but this time the power factor is leading because I see that here I have a negative reactive power, and I see that the power loss increases while the voltage is almost 120. So how we can explain this? So at the beginning, we had a resistive inductive component for this load, and we compensated the inductive component by having a capacitive component. But the capacitive component now is more than the inductive component, then the entire load characteristic is resistive capacitive. So we have a capacitive component in the current. So this is why the current increases, the power factor starts decreasing, but it is a leading power factor now. So what is the benefit from having such value of, let's say, compensation? We can bring the voltage to the rated voltage, but we are increasing at the same time the value of the current, which will increase the value of the power loss, the value of the power loss. So it's better to keep it at the full compensation level for this example. So I will keep it back to 2,250 bars. Okay. And I will run the circuit again. And as you see here, that this value of the voltage drop, which is 3 volts, almost 3 volts, can be compensated by having more voltage at the source. So if we increase the voltage at the source, so you can bring this value to 120. So this is the experiment about power factor correction. Of course, you can have the relationship between the voltage at the load versus the power factor. You can have the current versus power factor and the power loss versus power factor, and even the voltage drop, which is approximately the difference between the voltage at the source and the voltage at the load. So the approximate voltage drop will be 120 minus 117. It will be 3 volt, and you can have also the relationship between the approximate voltage drop versus the value of the power factor.